Hello, welcome to another problem session. This is another problem from website. Let me see. Okay. Physics bootcamp.org. You can get more information there. I maintain that website. If you have a question, you can email me or put in a comment under this video. Okay, so this is a pretty standard problem, but somehow it's quite confusing to students because this part is kind of flat, but the road is slanted, right? So when the road is slanted, you have to think of this like as if there was a cone, imaginary cone, and then it will make sense to you. This imaginary cone, and so this is kind of, it's trying to go in a circle of a cone, and so it is a circular motion. And so this is the center of that circle, and because this is a uniform circular motion, we will say it's a uniform circular motion for now. It has a acceleration, centripetal acceleration. If it was not uniform, then there will be tangential acceleration along that direction, along the direction of the velocity in that direction. So either speeding up, so acceleration can be that direction or in that direction, depending on whether slowing down or speeding up in the circle. But there will be always a centripetal acceleration. Okay, let's read. So we want it to not slide. So let's draw a picture. Here is a road part. So that's the angle that is called angle of banking, and we are drawing from behind. This is the view from behind. And this is just for a story, but this is the actual one we want, right? So you can see there's a friction along this tangential direction, right? And there's a friction along that direction. So there are two directions for friction. So friction can be along. This is the one that prevents it from going outward. So if the car is not to go flying off the road, the friction is static friction. We're interested is in that friction. And it says, what is the safest bend without sliding? So because we want the speed that we will be able to use it at some constant speed, we want it to be a maximum static friction that the condition can provide. Okay, and we don't want to exceed that. That's why we'll get the safest speed. So that's the static friction, and you can see the surface is this way. So the normal will be that way, but the gravity will be this way. Gravity will straight down to the center of the earth. So this, let's call this mg, and this is Fn. Now this is maximum, so this will be equal to mu s times Fn. Okay, and the acceleration we're interested in, this, all these forces will cause acceleration in these circles towards that direction, and that's the AC. All of these forces are in one plane, and of course there are forces perpendicular to the plane. One is the friction, let's call it into that direction. That's the static friction from road. So this is a static friction in that direction. Is this static friction? This is static friction, and this static friction are different. This static friction is as a rolling friction, and there is a, if this will only force, the speed will it will speed up, because in that direction it's going, it's going to speed up. The air drag, so there will be drag coming out. There's a drag. Then if they are balanced, then there V is constant. So we usually in this problem there is that situation there, these things there, and we don't normally talk about it. We just focus on this plane. So this is the plane we are focused, plane of forces and acceleration of interest. Okay, and there's a formula for this. Formula for this is v square over this radius of this circle. Okay, we can follow steps of calculation. So we've drawn the free body diagram, we identify the forces, and we looked at free body diagram. This is a free body diagram, and then we can pick axis so that equations can be easy to obtain. And I'm gonna try to use a interesting axis. We're gonna try this direction as x-axis, and try this direction as y-axis, just for, you know, having something different. If this is theta, then this angle is theta, then this angle is theta. So along the x, equation will be this is theta, so this is theta. So Fs max cosine theta is going to have a positive projection, because that's the positive axis. And this force and this force don't have any components, so this is going to be MAC, and in the y direction is going to be, oh, actually there is a normal force. Normal force has a x component as well, so this is Fn sine theta, and right side will become mv square over r. On the y direction, this will be mg, which is positive y is down for me, and so Fs will have positive plus Fs max sine theta, and Fn will be negative minus Fn cosine theta. And because acceleration along x-axis, there's nothing along y-axis, no acceleration component on y-axis, this all should be equal to 0. So this should be enough. We can fs max, we can replace that. We can replace that with mu fn and mu s fn. And then we can address both these problems. So we want to know v. For that I need to know fn, and I can get fn from here. So this is equation 1, equation 2. So equation 2 will give fn. And how do I get fn? Just bring these guys on this side and then divide, right? So fn will be mg cosine theta will become positive, mu s sine theta, and into 1 gives me mv square over r equal to mu s cosine theta plus sine theta. So you have a sine theta plus mu s cosine theta, and use fn, that makes it mg over cosine theta minus mu s sine theta. Okay, so that then m gets cancelled out from both sides, and r goes on the other side, and take a square root, get a v. So put r this side, this goes away, and a square root, the whole thing, v goes away. So that's the answer for A. We can put all the numbers there. Let me put the numbers and pause and give you the answer. Okay, so I did the calculation. I put it in all the numbers. In the calculator, I found it easier to do substitution, like find for sine 30 degrees and C for cosine 30 degrees, and then write these guys in a simpler way, so I don't have to do the whole thing, recall just S and C and these places. And I did the similar thing over here, and I got these values. Okay, this answers both A and B. Actually, another way would have been to just do the fn here, and just then plug fn here and solve for v. That would probably less work computationally because a lot of this thing got repeated when you do it this way. All right, just to recap, that in this problem, you don't need to get totally confused about things. When you're using static friction, when objects are moving around, then you need to ask about which direction static friction is really applying. And to address that, over here, I imagined what will happen if the static friction was not there. And when I imagined that, I found that car would veer off, go up the road. It will drive up the road, which means the static friction must be pointed down the road. Okay, so that's that was probably the main thing I find people confused about when they do a problem, which way the static friction pointed. Okay, so once I identified all the forces, okay, and realized that we don't need to worry about perpendicular, so we just ignore that part. and then we have to do free body diagram. The identification of forces led me to have free body diagram. And I just illustrated X and Y like that, which probably is not the best X and Y for this problem. But if you want to try using another X and Y, I might suggest you trying to use this. This direction, maybe X this and Y that, maybe Y that, and maybe X that. You might try to use that, because two of the forces will be along the here, right? So I won't have to I won't have to worry about, maybe see here I had to find the components of this force and this force and this force and this force. And often if you're trying to find the components of forces, not that you can't find the component forces, but it's usually error prone, because you might miss one of the forces which is not pointing towards the axis. If a force is towards the axis, hard to miss it. Okay, so I usually try to find the axis which most of the forces are pointed. Here I just point the axis where the acceleration was pointed. That's another strategy, but it turns out that strategy is not as good here as the one where you just do two forces. Okay, so with that pointer, you can I hope you can handle these problems and similar problems when you encounter them. See you in another video. Bye.